this is another closed process. In this process, air is being heated from a given temperature 300 Kelvin to a high temperature 1000 Kelvin, and we are asked to find the heat transfer and the boundary work involved. Now, initial pressure is 200 kPa, but you can very well understand the pressure doesn't change, because if you draw a free body diagram of the piston, you can see, again, this we have done in chapter 0, then we have a force of the weight on top and atmospheric pressure pushing it down, and the gas from inside pushing it up. So even though the piston moves because of heating, it is not accelerating, so there is no net force on the piston. As a result, you can show that because the outside forces, the forces downwards are never changing, these are all the same forces, the inside pressure must be constant. In fact, you can figure out exactly how much weight to place so that the pressure inside is 200 kPa. To do an experiment like that, you can figure the weight out and put that on the piston. Okay, this is aside. Now let's quickly draw let's say a TS diagram to show how the process will look like. And remember the constant pressure lines for the vapor in the superheated vapor region. So gas behaves like that, we know. So pressure remains constant. So it starts from, so this is a, let's say this is a pressure equals 100 kPa line. So, sorry, this is 200 kPa line. 100 kPa will be lower than that. So the process will be somewhat like that, going from state 1 to state 2, temperature increases. Okay, let's evaluate properties. But before we evaluate properties, let's get the equation we need to find the heat transfer and work. Delta U is given by Q minus WB, and in this case we cannot neglect WB because there is a lot of boundary work involved. So one way to find the boundary work, because it's a constant pressure, we know boundary work will be nothing but integral P dV, which is pressure remains constant, right? So if we can find volume 1 and volume 2, we know pressure, temperature, and mass. Ideal gas equation will give you those. So therefore we can find this directly. But I want to show you another way. Just suppose we didn't know enough information. Suppose we only knew temperature at the beginning and end. We can show that we can simplify this equation. How? Well, we can write this equation as mass times U2 minus U1, and Q minus WB is what? Pressure, V2 minus V1, correct? This is the boundary work. So therefore, Q can be written as M U2 minus U1, and we are switching sides, plus pressure, and let's bring the mass outside, so we get V2 minus V1. You get it? Because we know volume is nothing but mass times small v, specific volume. If you take mass common and manipulate this equation, you can write this as U2 plus P2 V2 minus U1 plus P1 V1. See if you agree. Because pressure doesn't change in this problem, so I can write it as P1 or P2. And if you recall the definition of enthalpy, we end up in a simpler formula. Q equals M H2 minus H1. And for the PG model, for so far it's model independent. It's simply Cp times T2 minus T1. If we go and pick up the value of Cp and Cv for air, so we go to the property tables, and for the PG model, common gases, for air, you can Cp is almost 1.005, and Cv is 0.718. Cp is 1.005, Cv is 718 in appropriate unit. So mass is 1 kg, Cp is almost about 1,000 minus 300. So the answer should be close to 700 kilojoule. We found Q, and now we can find W, because delta U is Q minus WB. We can use this equation. WB would be Q minus delta U. Q already found, 700. And this is mCV T2 minus T1, right? Delta U is m times U2 minus U1. Recall that. And U2 minus U1 for a PG model, by now you must know. Otherwise, go to table J and look up the PG model one more time, the formulas, you'll find that. And once we substitute these numbers, 1 kg, 0.718, 1000 minus 300, we get the boundary work to be about 201 kilojoule. There we go. So let's go and quickly verify these calculations. We go to test calcs and again follow the branch systems analysis closed, and we follow the generic branch uniform system and launch the PG model. The first thing, you have to select the gas, otherwise you cannot even enter any known variable. If you click, you cannot turn it on. So you have to go and select, let's say, air. Now the difference between air and air star is that sometimes, there's no difference really. The reference values are different. It will change your enthalpy, your internal energy, but in all problems you will notice we need to find the difference. So the difference will be the same no matter what you select here. So for state 1, we are given 200 kPa and 300 Kelvin. Mass was 1 kg. For state 2, pressure doesn't change, equals P1. Temperature is 1000 Kelvin. And of course, the mass doesn't change. So state 1 and state 2 are now calculated. We go to the process panel, load the states, the beginning state and final state. Notice the test calc already figured out that pressure remains constant. It found the boundary work. Other kind of work, which is shaft and electrical work put together, is called other kind of work in this test calc. Can you see? You can see the definitions are written here. There is no other kind of work, and that gives us the heat transfer in this problem. So the heat transfer is 702 kilojoules. Now you may think why the entropy generation is negative. That's because the boundary temperature is unrealistic here. This is something impossible. The gas is being heated to 1000 Kelvin. Boundary temperature cannot be 298 Kelvin. At least it should be 1000 Kelvin. You would have to agree. And if we have a realistic boundary temperature, notice entropy generation becomes positive. Also note, instead of 1000, if I make the boundary temperature to 2000 Kelvin, so look at the entropy generation right now, 0.5. You will see it will be much more. It's 0.85. In other words, now we created a bigger temperature difference. So there is more thermal friction. As a result, entropy generation is more because entropy generation captures the total friction in a system. So I stop here and invite you to solve more problems. Go to chapter 5 and find a problem you like, similar problem, and solidify your concept by getting the correct answer.